says like 20 seconds or so, I guess it'd be good to
walk out there.
Okay, if possible.
10 seconds.
But might as well go on over.
Okay, so it's my pleasure to introduce today's speaker. Kevin Hoffman is a fifth-year grad student here at Purdue. He works in programming languages and systems, and in the past he's also done some work on aspect-oriented programming, and he's proposed an original, highly scalable dynamic analysis technique, which he's applied successfully to Java programs. And in that context, he's also interested in applying it to security. Kevin is a GAN Fellow and a recipient of the Halstead Award, and I'll let him speak about his ongoing research for himself.
Okay, thank you. So this work is about ribbons, and it's joint work between me and Harrison Metzger and my advisor, Patrick Euxer. This is work in progress. We submitted a paper, and anytime you have questions or something isn't clear, please stop me and ask the question. Make sure it's fully clear. So just talk, we'll give you some background, go through the concept, present our extension of Java language, which implements this concept, some of the system details implementing it, a micro benchmark we have from our system, and then current work and ongoing work. All right, so this is a security seminar, and I'm interested in practice, solving problems. So here we have from the MITRE Corporation a categorization. They looked at all the vulnerabilities, and they pulled out patterns, the top 25 most dangerous errors people make to introduce security failures. And if you look at these, a surprising number of the top 10 are due to data validation or formatting errors. And if you look at some of the possible countermeasures to the data validation formatting errors, the techniques, there's no sure solution. The techniques are all sort of spread throughout the code. They're difficult to implement. So for example, you have to track data flow. Is this variable that was received, could it eventually be used directly as part of the SQL string? And if so, have I properly formatted already or not? Or character encodings are really subtle. So if input's submitted with the wrong character encoding, it could miss, certain special characters that you're scanning for could be missed, and later when you transform the character encoding, those special characters could appear again. So it's pretty difficult to solve these, obviously, as they're a large part of the top 10. So systems typically have defense in depth. There's other mechanisms that are more general that try to mitigate what happens if they make one of these failures or errors. So one of the common principles is called least privilege. And the idea is just that you want to give the security subject the least amount of privileges necessary in order to do whatever task they need to do. Sort of damage control, if you say. Also, you want to make sure that your granularity is fine. So, if you have least privileges for your entire operating system, obviously that's not so useful. So if you have it at your process level, then the process is compromised. Anything the process could do, the attacker would be able to do. But if you can get even finer than that, it mitigates your scope of the attack. So the finer the better. The more often, from a security perspective, that you're switching, what set of privileges you have in a secure fashion, the more you can control, put security boundaries here. So some of the systems out there, in practice, operating systems, you've got discretionary and mandatory access controls inside of operating systems. ACLs, SE Linux provides a sort of type enforcement mandatory access control system on top of regular ACLs. However, these just deal with operating system resources, files and network sockets and these types of things. But what about the heap? what about all this sensitive, potentially sensitive data inside of a process? What is there to protect the heap? But okay, so keep this question in your mind, and next consider, does the heap even matter? So, if we look further in the top 25, here are areas from the top 25 that are related to heap corruption or heap manipulation. So about 1/4 of the top 25 is related to heap problems. You've got your classic buffer overflow, buffer overruns, improper validation of array indexes, various problems with buffers. And these cause serious problems. So here's another list from the SANS Institute that shows you the top 6 zero-day vulnerabilities for a 6-month period back in 2009, according to their classification. Yes.
So you're focusing on Java, so doesn't Java protect against buffer overflows? So that is the one we got.
Yes, so Java does protect against it, like you say, or any managed language. However, you still have a fair amount of code written in the native language implementing the Java virtual machine, or you have plugins that are native. And our technique, even though we've implemented our language extension in Java, you'll see later in the talk that it actually applies at the operating system level, the process level, and then at the JVM level and the language level. But true, all of these vulnerabilities here, the zero-day flaws, these are all native code plugins for browsers. So focusing specifically on this browser plugin problem, one solution, Internet Explorer, runs in a sort of lower privileges mode. It doesn't have access to most of the file system. But what if, if there's a flaw in one of these plugins, you still have the vulnerability of tabs or different domains accessing each other's data. So once the plugin is compromised and the heap of the process is compromised, that malicious script is free to go steal your credit card number from the banking tab you've got open at the same time, for example. So you can run plugins out of process, and Chrome does this, and Firefox is starting to do this. However, it makes the code much more complicated. It's a little bit less efficient, and it also makes things a lot more complicated when you want to have multiple plugins of the instances of the same plugin. But yet these plugins need to share some mutable state together. So what we're really after is this robust access control mechanism over the heap. So taking this example further here, say that we have Firefox open, we've got 2 tabs open. Each tab has some Flash scripts inside of them. So on the left here, I've divided up the heap into different protection domains, as we call them, or just segments of the heap. Maybe your browser has some global private state that it uses for its own purposes. It's got some shared state, maybe the cookie data or the cookie cache or image cache or whatever it may be. You've got your document object model for each tab. You've got your specific Flash scripts running in each tab, each with its own state, probably running on its own thread depending on how Flash is set up. And then you've got, any Flash specific caching or shared state. All right, so, what does tab 1 need access to in order to perform its work? So you've got its own document module, any scripts running inside of it, and the global private and shared state. But not all of these regions are created equal. So here you've got, highlighted in red, a region that you may not want to have writable or perhaps even fully accessible by the thread running the tab, the first tab there. So how do we model these privileges and still have an efficient yet easy to implement and easy to write system? So there's some prior work on heap protection. Nooks is sort of a special purpose system for protecting device drivers inside the operating system, and it provides a sort of fixed structure for protection domains for device drivers and the different parts of the operating system. And we're after a more general purpose mechanism, You've got Opal, which has just a single shared virtual address space across the entire operating system. So each process doesn't have its own, and it's partially shared. They took a slightly different approach. They have a sort of dynamic grant and deny model, so it's hard to provide sandboxing inside of this operating system. Software isolated processes typically have high overhead and or limitations, more of a static protection domain structure. You've got mechanisms that rely on hardware modifications. We're after just standard hardware out there, Intel, AMD, and a couple of others we could discuss in detail. All right. So just in case this work isn't entirely about security, we're also interested in performance implications. So the world is changing. We're going back towards more of a NUMA architecture. You've got the CUDA framework from NVIDIA, program on the graphics cards plus the processor. Intel's got this research 80-core chip out there. How does an operating system do game scheduling over 80 cores efficiently? It's a difficult problem. So essentially, we want to provide the operating system hints. If you can carve up a processes heap into these regions, and the operating system knows how they're structured and tied to each other, then it knows, okay, this sort of cluster of threads over here, I can put this on cores, on the top left part of the grid, as opposed to this other part of the program. And so that's another motivation for this work. So getting more into what we're proposing here, which we entitled the ribbons concept. The first concept is just this idea of protection domains. So divide up the heap into disjoint protection domains, and then you have these privileges. Read, write, it's pretty typical, and then inject. So inject just means something is able to allocate a page or an object of memory inside of this protection domain. All right, and then privileges are between protection domains, and they're modeled as tuples, with the typical source, privilege, and target, just enumerating the list of all privileges in the system. All right, so here's a diagram going back to our example. We've got, the Firefox global state, private state, the DOM, the two different tabs, some scripts, and the Flash plugin. So I'm modeling with these arrows, the tuples. So the source to destination with the privilege. So you can see here that the Firefox global private state has full read, write, and inject access to the global shared state, but the shared state can perhaps only read from this private state. And I'm sure that the actual Firefox browser would be a little bit more complicated. I'm just abstracting here to get the concept depicted. And then we sort of divided the rest of the browser into these layers where you've got the shared state, the document object model, any plugin state like the Flash scripts, and any shared state between the plugins. All right, so that's what protection domains is about. And now we get to ribbons. So a ribbon is a grouping of threads, and there's a process has one or more ribbons, and each ribbon has one or more threads. And so each ribbon sort of lives within a set of protection domains. And usually it's just one protection domain. But essentially, you can just think of it as, this ribbon is a sort of security context. When I'm executing within this ribbon, I have the privileges that my current domains that belong to this ribbon have as the source part of my tuple, my permissions tuple. All right, so going back to this example, we're just highlighting here some of the ribbons that you could have running here. So your browser configuration ribbon, and it's tied, it lives within this global private state, and so it's got read, write, and inject onto the Firefox global shared state. The ribbon that lives within this other protection domain, it only has the privileges that this source protection domain has, and so forth. Okay, so here we have, notice this ribbon doesn't encompass the entire layer, but instead it just encompasses one of the tabs. of the browser, one of the document object models. And so instead, it just has the privileges, again, associated with that one particular instance of that protection domain. Okay, and etc. Here's the one for the Flash plugin. Okay, so here's the concept, but how do we provide isolation guarantees over this model? So what's to say that we couldn't create a new protection domain, and that new protection domain couldn't request privileges? Script 2 couldn't request privileges on script 1. How do we structure the access control mechanisms to prevent that from happening? So we define these two possible conditions here. We've got the first condition, it's the acquiring condition. So you can think of this as as a ribbon, when I create a new protection domain, I can't acquire more privileges than what I currently have. I mean, that's almost too obvious to have to say explicitly, but it just says I can't get more than what I have. The granting condition is a little bit more subtle. It says when a new protection domain is created, I can't grant to another protection domain that already exists privileges that it doesn't already have on the ribbon that's creating this new protection domain. And I've got some figures here to help us get these two conditions cemented. All right, so take this tab number 1 ribbon. It's loading the page. It knows it needs to create a Flash plugin, so it's going to create a new protection domain for this Flash script on this tab. All right, so what does it want to do? First, it wants to acquire privileges on this new protection domain. So, the script is trying to acquire, read, write, and inject privileges on the document object model, which is fine because, the creating ribbon itself, has privileges on itself. So that meets condition 1 for acquiring. And then also, it wants to acquire privileges on the Flash global plugin state. And notice that the document object model ribbon there does indeed have those privileges. And so the new protection domain is allowed to acquire those privileges. All right, so the opposite. The ribbon, the tab 1 ribbon, wants to grant to this new protection domain, these privileges. It wants to essentially give privileges or grant privileges to this new protection domain. So, of course, it can grant it to the new protection domain. That's just a given. But then the Flash plugin global state also wants to grant privileges to this new protection domain because it's required for proper operation of the browser. And it's allowed to do that because it does have, the Flash global plugin state does have privileges, those privileges already on the creating ribbon, which in this case is the tab number 1 ribbon. All right, so here's something that isn't allowed by condition 1. Back to the acquiring restriction. So, say that script number 1 tried to acquire privileges on script number 2. Well, it couldn't do that because the creating ribbon, tab number 1, doesn't have those privileges. And so it's prevented from doing that. Okay, and the opposite, say that script number 2 tries to request privileges on the new protection domain for script number 1. Well, it can't do that either because it doesn't have privileges on the ribbon that created that protection domain. And so with these two properties, you're able to provide full sandboxing of protection domains that you create. You can create sort of a layered hierarchy that ensures that anything, once you create a ribbon, those privileges are sort of fixed except for any new protection domains that it creates. But even any new protection domains that it creates won't be able to connect to and access data outside of that. And so that's a strict hierarchy. But there's also a level in between we call cooperative isolation, where a new protection domain can grant privileges to other existing protection domains, but only the new protection domain can be the one granting. So essentially it can say, I know that I want to be able to give somebody else permission to access myself. And you can say to create a sort of shared area where two different segments of your browser could communicate. For example, this global state that you saw. All right, so that was the concept. Now, how do we make this easy to program for? We chose Java as a language to first extend this in. We call it Ribbon J. All right, so we wanted to be backwards compatible, make it as easy as possible for existing programs to work on this. We wanted to make heaps first-class objects, so we didn't want some new type of concept in the system, just reuse the existing class and object ideas. We also want to provide, leverage the type system to model these sort of patterns or types of protection domains that we saw in our example. And we also want to be able to provide enough structure to enhance, static analyses, for example, alias analyses, given this particular object and these two threads, which exactly, which variables could actually point to the same object in the heap. Are they alias to each other? So first we expose this protection domain idea with this new keyword, which is used at the same level as a class declaration. So you're defining a new type. It's a protection domain type. All right, it accepts arguments which model which domains this one is going to interact with. And then inside of it has a list of rules. Okay, how do I grant privileges, or how do I acquire privileges, or in the language it's called require privileges from other domains. All right, so so a reminder, here's our example again, but I've colored the different protection domain types. I mean, it's pretty intuitive, but you've got your own type for the state, the shared state, the DOM, the scripts, and the shared plugin state. Each of those are modeled with its own type. Each type can have one or more instances created of that domain at runtime. All right, so here's what the code looks like. Pretty similar to class declaration. You start out with the protection domain keyword. This global shared domain accepts an argument. So the global shared state, it needed privileges from the private state, and it also needed to give privileges, allow the private state to have read, write, and inject access on it. So the way that this is modeled is through these grant and require statements, and it's pretty intuitive. You just say, grant or require, the set of permissions, and then the named argument defined in the protection domain line, which domain that you're referring to. And so these are sort of templates. How do I structure this protection domain statically, and then at runtime, these things are instantiated just like objects, and the parameters are filled in, so the connections are actually made to these other types at runtime. So continuing the example, the global shared state also required the Flash plugin global state. It needed to give read, write, and inject privileges to and from. So when we model the plugin global state, because it's created presumably after the browser global state, so back in the definition here of the global shared domain, the plugin domain didn't yet exist at this point in the program. So that's why we couldn't reference that plugin domain yet here in this declaration. But instead, we just grant privileges. Once the domain is created, then it says, okay, grant privileges to this browser shared state onto myself. And so this way, and that's why both grant and required in the require statement have to be in the language. All right, in the slightly more interesting case, you've got the DOM domain, which has layers both on top of it and below it. And you just see that it accepts two arguments, and we're essentially giving all privileges, these bidirectional privileges on all three types to each layer. All right, and then finally you've got very similar for creating up your script domain here. So how do we model ribbons in this language now? So a ribbon is an extension of the thread group class. Thread group, just like it says, it's a named collection of threads. You can stop, start, deal with the threads as a group, give them a name. And a ribbon also sort of acts as its own protection domain. So implicitly, it's got its sort of own little private area for it to work with. Any ribbon local data. And then similar to protection domains, it will accept a named argument list of protection domains that it's going to live within. And the first protection domain on this argument list is called the default domain. Any allocation that happens that's not annotated will be put onto this default domain. And then similar to this, to get the current object, you've got this ribbon to get the current ribbon context. All right, and then we extend the new operator. So these ribbon objects, essentially, in protection domain objects, the protection domain objects represent the heaps as first-class objects. The regular Java objects that happen to be, associated with some area of your memory. And then the new operator can optionally accept a protection domain as an argument, so you know which protection domain you want to allocate within. Okay, so going back to this example here of ribbon creation, how would this look like in the code? So recall the definition, the declaration for this protection domain, the DOM domain, the document object model. So it accepted the global shared domain and the plugin global domain. So you can see here, it's tied to the browser global state, and it's also tied to the Flash global state. All right, and so then we model this ribbon. Just with the ribbon keyword, we're declaring the new type. It accepts one argument because you can see here that it's only living within one protection domain. It's living within one protection domain for this document object model. So it only has one argument. All right. This particular tab might have a list of scripts that it's associated with, and then say that we wanted to start as Flash script. So what would we do? First, we'd create a new protection domain at runtime with this particular type, and we'd connect it to the ourself, so the DOM for the document object model domain, and then the document object model domain is also associated already with this browser, with this Flash global domain state. And those arguments, notice, are exposed as fields, so that we can just use the instance of that protection domain DOM .p, which is referring to the argument of the protection domain. All right, and then here we just create the ribbon object like normal, but notice we've got this new where keyword here. So the where keyword essentially just instantiates the ribbon argument list with the concrete set of variables, protection domains, that it's going to live within. In this case, the script ribbon just lives within one domain, which is the new domain we just created for it. And just to show you the syntax, I've showed you here how you could specify which protection domain you want to allocate within by putting in angle brackets after the new keyword, some protection domain object. In this case, that doesn't actually do anything different because the DOM protection domain is the first protection domain of this DOM ribbon here. So had we not specified that explicitly, it would have taken that first argument on this ribbon as the ribbon to use for allocation anyways. All right, and then we just treat these ribbon objects like normal, so now we can add it to our list of script ribbons, and then we can actually start the new point of execution, the new thread that's going to live inside of this new ribbon to run the Flash script and put it into the thread group of this ribbon. All right. So now let's move on to how do we actually implement this. Right now we only have it implemented inside of user space, so it's obviously only secure for a managed language where all the native code is fully trusted, and we're currently working on a kernel extension. So So here's an overview of how we implemented this inside of user space. We're using regular operating system, virtual memory manipulation commands, mmap, mprotect, munprotect, to establish these protection domains. We also have our own sort of area of the virtual address space for our metadata, which we attempt to isolate apart from the rest. And then we also enhance just the malloc and free calls of the glibc. So we override those to understand protection domains. So the malloc and free calls, they just use the default protection domain associated with the current ribbon. And we also use the clone operating system call to sort of create a new ribbon with some special semantics that we'll look at. So a protection domain is modeled as, in the metadata, as one or more contiguous regions of pages. Pretty straightforward. It also just tracks, those tuples for my current domain. Which privileges do I have on the target domains with each privilege type. All right, and then control memory domain, the metadata. One important point to note here is that when we start up, we pretty much take over the entire virtual address space available to the process. So normally the glibc allocator would use something like an sbreak or mmap perhaps to grab more pages from the operating system. Instead, we're replacing that with their own, and we're just assuming now we can take up everything that wasn't taken up by the text and the code segments and the data segments of the program. And this metadata, obviously, since we're in user space, we can't provide, we can't prevent native code from manipulating this, but we do try to prevent random corruption by, when we're not inside of the ribbon library, we just sort of unmap that region of memory so it can't be corrupted inadvertently. Okay, so how does allocation work? We've got 4 layers here. So you've got the application layer at the bottom. When you call malloc or a custom malloc that lets you specify your protection domain that you want to allocate from, we implemented our own custom slab allocator. Any algorithm could have been used, but essentially you've just got this custom allocator that's manipulating a region of pages. And so the protection domain allocator only works with pages. So you can say, I need X amount of memory, and it says, okay, here's another contiguous region of X pages. And the same is true for freeing. So when the slab allocator understands, okay, this region of memory is now completely free, it tells the layer above it or below it, depending on how you look at it, you can release these and reuse them for some other protection domain. And then this is all implemented on top of mprotect. And then, of course, the malloc also has to be modified so that we can enforce the inject privilege, so that a ribbon that, it makes sure that a ribbon does have permission to allocate within a particular protection domain. And likewise is true for freeing, of course. So how does this work? How do we make this efficient at runtime? So we've got these different ribbons. They have different page table entries, so they each have their own sort of mapping of virtual memory to physical memory pages. There's 2 different strategies how you could approach this. You could say anytime that a protection domain allocates new pages, I need to have any ribbon that has access to that protection domain immediately, map in that memory into its virtual memory space. However, if you have ribbons that have access to a lot of different protection domains, but they're only using a small portion of it, for a large portion of the time, you're wasting a lot of energy, because then you have to go through several ribbons, update all of your page table entries, which could potentially have cache effects. So it's fairly expensive. So instead we take this lazy strategy where all memory in this virtual address space managed by our library is completely unprotected. Anything you touch in there is going to hit a seg fault. And then we modify the signal handler so that when we get the sig-segv signal, we just check that address space. We have this reverse map, which protection domain is associated with this virtual address. Okay, and which ribbon am I currently running on? Okay, and does this ribbon actually have access to this region of memory, this protection domain? And if it does, then it asks the operating system, now please map in this page and a series of pages around it, and then it restarts the program, and it never knows the difference. So the first time you access that, it's going to induce this this signal handler, but after that it's going to be just as fast as it never happened. So we'll look at some micro benchmarks later, to see what is the actual overhead of this. All right, and then finally, when we create a new ribbon, how do we actually ask the operating system to do this? And Linux is pretty handy because instead of having just your normal, fork and exec calls, you've got this clone call where you can tell it, okay, I want to share, the file table, my list of open files, but I don't actually want to share the page table entries, the virtual memory, the virtual address space. So that's exactly what we did. So you've got ribbons, they share the same resources, the same file table, except they've got their own private virtual address space. And then how do we bootstrap a new ribbon? So pretty much the new ribbon just sort of unmaps everything because it may not have access to everything that the creating ribbon had. It turns out it was a little bit trickier than that because when we were inside of this virtual machine, this Java virtual machine, it sort of expected, it had its own sort of custom logic in the SIG-SEG-V handler, and we needed to allocate a few of the first pages, especially the text pages that it was going to start running on ahead of time. So there was a few tricks down there. All right. And another interesting detail was when your program is first loaded into by the operating system and first starts executing, you get all these different segments. So you've got your text segment and your data segment and your read-only data segment, and then when you load shared libraries, each of those has segments, and those are all mapped private to the process by default. So we have to go through and every time we load the program or every time we load another shared library, we have to take those regions of memory, copy them aside, unmap them, remap them to be shared across all ribbons in our group, in our currently executing process, the group of ribbons, and then copy the data back. However, this got a little bit tricky because the shared library that has some of these mmap and mmmap calls actually can go through a virtual pointer first, which lives inside of the data segment. So if you, when you're unmapping that, and then you suddenly try to make the call to mmap, it's going to hit that virtual pointer, which was stored in that unmapped space you were trying to remap. And so what we had to do was actually copy that, copy all of the code as well, rebase all of the pointers inside of that copied code to use our new data segment that was in this temporary data segment, jump to this special function in the new copied text segment. Then we can unmap because it's using the rebased virtual function pointer, which is in our locus side, our temporary copy of the data segment. So a little bit tricky to do it in user space that way. All right, and then inside of the JAX virtual machine here, we have two layers. You've got your front end, so your typical extensions to your lexer and your parser. We really like to use the JASTAD framework for this. We found it's really clean, provides a sort of aspect-oriented and declarative style for modeling attribute grammars. It's fairly straightforward. And what it does, it takes all these language extensions and it rewrites them to use the internal ribbons API that we implemented inside of the JVM. And so one of the interesting points here was that, how do we modify the new operator? Because we don't want to modify the Java bytecode because that would require, that would break Java compatibility. So instead what we do is The API provides just a static method call that indicates, okay, the next allocation on this particular thread should use this particular protection domain. And so I was sort of setting a thread local variable for the next allocation to happen. All right, and then garbage collection obviously just has access to everything, so we were using a stop the world garbage collection. So everything stopped except the garbage collection thread had access to everything, cleaned it up, and then the program threads, mutator threads, continued normally after that. All right, and then we merged our custom signal handler with the Java virtual machine signal handler, and we also they also had a mechanism to propagate memory errors. For example, they do null checking using signal handlers. So we extended that to actually be able to throw a Java exception if a particular thread tried to access memory that it didn't have. So your program won't crash hard, it'll just throw a runtime exception at that point. So, you know, how do we measure, you know, just at least just one measure here of performance. So here's a slightly simpler example than the browser example. Just imagine you've got this master worker type model, which is pretty common in embarrassingly parallel applications in scientific computing or elsewhere, where you've got a master who's filling up and controlling some queue of items that need to be processed, and then you've got one or more workers, you know, operating on different threads that take things out of the queue, do some sort of work on them, and then put the results back into the queue. So how would we structure protection domains for this? So we've got, you know, the master private state, which the workers should need to know nothing about. All they care about is doing their work. You've got the queue data, so the master is the only one who's allowed to actually put items into this work queue, modify things in the work queue, the actual things that need to be done. So the different workers can't manipulate, you know, what its other worker is going to be doing or what the master wanted it to do. But it does need to have write access to the queue control area, what's actually on the queue, because obviously a worker will have to take something off the queue, so it can't be completely isolated. So we separated these out. All right, and then the way we modeled it for a micro benchmark is we just had 32 megabytes of data, and we varied the item size. So each item was different sizes, ranging from 4 kilobytes to I think 4 megabytes. You know, however number of items it took up to fill 32 megabytes. And we wanted this to be a memory-intensive bandwidth rather than CPU-intensive. So we just the only thing that the worker does when it consumes an item is it copies it and then it sums up everything inside of that just to make sure that we've actually touched everything. The JVM hasn't optimized that out. So here we've plotted the original JAX RVM virtual machine unmodified in blue, and then we've got our modified ribbon virtual machine running with our custom ribbon, you know, the code enhanced with our ribbons, plotted at 99% confidence intervals, and the confidence intervals always overlap. So essentially you've got no noticeable performance impact, which of course we would expect because the only overhead you're actually hitting is the first time, you know, the ribbon accesses a ribbon accesses a page, you've got that extra signal handler, but after that, you know, in this example, it's very stable, and there's no extra signal handlers being called, and so there's no overhead. So it just sort of validates that, you know, there wasn't any funny behavior introduced by our approach. And this is the same test here. It's just showing throughput in megabytes per second. So interestingly enough, you know, as you would expect, smaller the queue item size, faster the number of items you can process per second. As items get larger, you know, you're doing more work actually doing memory-intensive operations rather than manipulating the queue, and so your memory bandwidth goes up. All right, so just to conclude here, we've covered our proposed idea of ribbons to provide this sort of access control mechanism over the heap that's also works on existing standard hardware and is efficient. We also believe this is the first language extension where you have these type protection domains that are instantiated at runtime. So you've got this flexible dynamic memory segmentation model. We've never seen the inject privilege modeled explicitly before in the language, and also this idea of adaptable isolation levels. Finally, this is ongoing work, so we are working on a kernel extension so we can actually provide security for native applications, move all of that metadata into the kernel, and also get those performance optimizations we were talking about, get the kernel scheduler aware of the ribbons. Another important, that we feel is important for securing existing applications is being able for the same thread to securely switch which ribbon it's currently executing on. So for example, Firefox, at least in 3.5, is single-threaded mostly. So it would have a hard time. You'd have to re-architect a fair amount of the code just to enjoy the benefits of ribbons. And so instead, we're investigating techniques. How do we securely provide a mechanism to switch into a more restrictive ribbon and know when it's safe to actually switch back out without being manipulated? And so one possible technique that we're looking at for this is module boundaries. So when you load the shared object for the Flash player, for example, it's going to have its own different address space. And so you can take advantage of that, of those known boundaries, and unmap those text segments so that when you do the switch, you can automatically switch ribbons, for example. And we're just investigating the details. How do you, securely switch back? Do you have to have, you probably have to have different stacks for each of the ribbons, and if you do, when you make a call between them, how do you know how much of the stack to copy in order to get the arguments for the cross-ribbon function call to come across correctly on the stack? And the same thing about functions that return data. There's also the complicating factor of callbacks. When the Flash plugin, if it needs to manipulate the DOM or tell the browser open a pop-up or whatever, how does it call back out of its isolated ribbon and actually execute that callback inside of a different ribbon and then switch back? And so we're looking at how to structure these calls in a secure fashion, but yet isn't too intrusive on actual code. So that ends the presentation. So be very happy if there's any questions. Patrick?
Can you comment more on the symmetry or lack thereof between grant and required permissions?
Yeah, so I guess one common question is why do you actually need a grant and require? And that's more of a function of the RibbonJ language. So our actual implementation only understands the grant ability. You're just granting from source to the target. And the key thing is when you're constructing a new ribbon, right now the initial protection domain is constructed, and then you grant all of the relevant permissions on that domain, and then you make a call to put that new protection domain into isolation with the given isolation mode. So at that point, that's when the restrictions on the grant operations take into effect. You're sort of locking it down at that point. Any other questions or ideas for application, thoughts? Any skeptics?
You said if you unmap these pages when you're not in the particular library, you also unmap them like on a timer interrupter or whatever, when you're just, not when you're returning from the library, but when you're just switched out incidentally?
When you're switched out incidentally, like just switching to another process, I think you would just leave things the way that they are, because when you came back, it would restore your same page table entries, and then you'd still be operating within that same ribbon, but of course you'd still be at the same point in the code. Your instruction pointer would be the same. So we haven't yet encountered a place where we need to do that on a timer yet, at least. So, yeah, I guess if there's no further questions, we'll just end here then.